Welcome to Chapter 6, the final chapter of our spectroscopy series. Here we bring together everything you've learned by automating spectral analysis with Python. We'll build practical tools for loading spectral data, performing baseline corrections, detecting and fitting peaks, and creating publication-quality visualizations. By the end of this chapter, you'll have a complete toolkit for processing UV-Vis, IR, Raman, and XPS data programmatically, enabling reproducible analysis and batch processing of large datasets. The first step in any analysis pipeline is loading data from various file formats. Spectroscopic instruments output data in many formats, from simple CSV and TXT files to proprietary binary formats. We'll create a universal loader that detects file types and converts them to a consistent pandas data frame structure with wavelength or wave number, intensity, and metadata columns. This abstraction layer means your analysis code works identically regardless of the source instrument. Libraries like NumPy, Pandas, and SciPy form the foundation of our data processing toolkit. Baseline correction removes unwanted background signals from spectra. We'll compare 4 common methods. Polynomial fitting works well for smooth, gentle baselines, but struggles with complex shapes. Asymmetric least squares, or ALS, uses iterative fitting with asymmetric weights, excellent for spectra with sharp peaks. SNP, the statistics-sensitive nonlinear iterative peak clipping algorithm, is robust for various peak types. The rubber band method connects minima like a rubber band stretched around the spectrum. Each method has parameters to tune, and the best choice depends on your specific spectral characteristics. Automated peak detection identifies features in spectra without manual inspection. The SciPy signal find peaks function uses prominence, width, and height parameters to locate peaks reliably. Once detected, we fit individual peaks with Gaussian, Lorentzian, or Voigt functions using SciPy, optimize, curve fit, or the more sophisticated LM-fit library. Multi-peak deconvolution handles overlapping peaks by fitting multiple functions simultaneously with constraints. Output includes peak center, amplitude, full width at half maximum, and integrated area for quantitative analysis. Talk plots extract semiconductor band gaps from UV-Vis spectra. The analysis converts absorbance to the absorption coefficient alpha, then applies the Talk equation. Alpha times h, nu raised to the power n, where n equals 2 for direct band gaps and 1/2 for indirect transitions. Plotting this transformed quantity against photon energy produces linear regions. Extrapolating the linear portion to the x-axis intercept gives the band gap energy. For example, zinc oxide shows a direct band gap of about 3.3 electron volts. Python with NumPy makes these calculations straightforward and reproducible. Machine learning enables automated spectral classification and identification. The workflow begins with feature extraction, converting spectra into numerical vectors, capturing peak positions, intensities, ratios, or principal components. These features train classifiers like random forests, support vector machines, or neural networks using scikit-learn. Model performance is evaluated using confusion matrices, showing classification accuracy, and ROC curves indicating the trade-off between sensitivity and specificity. This approach enables spectral fingerprinting for material identification, quality control, and authenticity verification. Real-world analysis often involves processing hundreds of spectra. A robust batch processing workflow iterates through input files, applies consistent processing steps, and generates organized outputs. Using Pathlib for file handling and TQDM for progress tracking makes the code clean and informative. Each file passes through loading, baseline correction, peak detection, and quantification before results are saved as CSV files and PNG plots. Error handling ensures that problematic files don't crash the entire batch. Parallel processing with multiprocessing can dramatically speed up large jobs. Static plots are limited when exploring complex spectral data. Plotly creates interactive visualizations with zooming, panning, and hover tooltips that display exact values at any point. Subplot layouts show the main spectrum alongside derivatives and residuals simultaneously. Range sliders enable quick navigation through wide spectral ranges, while drop-down menus allow selection between multiple spectra. Interactive plots export to HTML for sharing or can be embedded in Jupyter notebooks. These capabilities transform how you explore and present spectroscopic data. Let's see a complete XPS analysis pipeline in action. Step 1 loads the spectrum from file. Step 2 reads the survey spectrum to identify which elements are present. Step 3 extracts high-resolution regions of interest. Step 4 applies iterative Shirley background subtraction, the standard baseline for XPS. Step 5 fits peaks using constrained Voigt functions. Step 6 quantifies composition using relative sensitivity factors. Step 7 generates a PDF report with spectra and composition table. The entire pipeline executes in roughly 8 seconds, demonstrating the power of automated spectral analysis for high-throughput workflows. Congratulations on completing the Introduction to Spectroscopy series. You now have a comprehensive toolkit spanning 6 chapters. Chapter 1 covered light matter interactions, Chapter 2 UV-vis absorption spectroscopy, Chapter 3 infrared and FTIR techniques, Chapter 4 Raman scattering, Chapter 5 XPS surface analysis, and Chapter 6 Python automation. You can now combine these techniques in integrated workflows for complete material characterization. Revisit the code examples in each chapter and the reference textbooks listed there to continue developing your spectroscopy expertise.